So we're starting by factoring this one. It's basically riffing off of the same stuff we were doing yesterday. And based off that work we did yesterday, we can already know that since it's a trinomial, and since it goes x to the 8th, then x to the 4th, notice our first exponent is double our second exponent, and there's no x in the last term, that yes, we can potentially go ahead and factor it just like we do a quadratic. It's just that each of the binomials that we factor it into are going to start with x to the 4th here, instead of just plain old x. And so we use the same technique. We want to look for two numbers that add to the middle number and multiply to the last number. There is such a combination that adds to negative 17 and multiplies to 16. It's negative 1 and negative 16. The question at this point, though, is can we factor it any further past this? Yes. And the answer here is actually going to be a yes. And that's what makes this problem a little bit new and a little bit different, is the factoring that we can do from here. So looking at that first one, the x to the 4th minus 1, you might be thinking, well, it's a lot like the sort of thing that I could factor into x plus 1 times x minus 1, like this. But of course, if I factored it into that, I'd end up with x squared up here rather than x to the 4th. So a solution that we might naturally try then is, well, what if I made both of these squared? Because x squared times x squared would give me x to the 4th. The question is, would that give me x to the 4th minus 1? And let's actually just take a quick moment and check that. So x squared times x squared minus 1 times x squared plus 1 times x squared minus 1. You'll notice here the minus x squared and the plus x squared do in fact cancel each other out. So yes, it does equal just x to the 4th minus 1. So yes, that works. We can go ahead and factor it like that. You're going to be able to factor the x to the 4th minus 16 similarly. It's also going to become an x squared minus and an x squared plus, because we're subtracting a perfect square here. And so when we factor that, you end up with this. And yet we're still not done. Take a look at each of the binomials we have at this point. Some of them can factor further. So in order to answer this part, it's a matter of remembering how do we know what can and cannot be factored when we're looking at quadratic binomials like these. And remember, the key when factoring a quadratic binomial like these, we have to be doing x squared minus a perfect square. And so that already means that the x squared plus 1 and the x squared plus 4, those can't factor down anymore because they're addition. Remember, we only even have a chance at it if it's subtraction. And even then, it has to be subtracting in perfect squares. So, x squared minus 1, can that factor? Yes, it can. Because 1 is a perfect square. It's 1 squared. What about the x squared minus 4? Will that factor more? Yes, it will. And so, we're going to go ahead and factor those two. And when we do so, notice each of those binomials will break up into two more binomials. The two that we can't factor further, notice they just carry down exactly as they are. So it's going to stay in x squared plus 1 and an x squared plus 4 in our final factored form. So the stuff we can factor further, we do. And so when we do that final factorization then, this is what you should be looking at. Now make sure you have it written down correctly, because we are going to come back to this problem later on during today's lesson. So next up, we're going to be finding zeros of polynomial functions. Now we've done zeros before. We've done finding the zeros of quadratics many times, because remember, the zero of a function is just what can you plug in for the y value, or plug in for x that makes the y equal 0. And so, for that first one, it looks somewhat familiar. Because if you just took a look at two sets of parentheses and we're setting that equal to 0, that's just what we did with quadratics. The process when there's more than the two sets of parentheses is going to be the same though. That's the great part about this process. And so I'm going to look at each of the sets of parentheses and say, what can I plug in for x that makes it equal 0? And so like in this first parentheses, if I plug in -1, then that whole thing becomes 0. And 0 times all of the rest of the stuff, no matter what that is, 0 times it, of course, will have to be 0. And so one of my answers then has to be -1. Of course, the others, 5 and -6. Same basic idea as when we did it with quadratics. All right, so taking a look at the second one, most of it's pretty straightforward where we have all the parentheses. The part where any questions might come up is what about this out front? We have an x multiplied out front. When we're doing our solving with quadratics, we sometimes had a number out front. So we might be like multiplying the whole equation by 4 or something like that. And we found in that kind of a case that when I was just multiplying by a number, it didn't change my answer. And it didn't give any new answers or anything like that. In this case, however, that's going to be a little bit different. Because when you just have a number out front, there's no way to make 4 equal 0. Because there's no variable there to plug into. But here, with an x multiplied out front, there is a variable. There actually is something we can plug into. And so, what would I plug into x here that would make that equal 0? 0, yeah. And so, we actually end up, when you have an x that's by itself like that, having a 0 of 0. And then the rest of them are all the same as what we would expect from the parentheses. Okay, for the third one, we have x minus 8. Okay, well, obviously then that's going to give me 8, right? But it's squared. What does the squared do? Well, remember, x minus 8 squared means x minus 8 times x minus 8. So, in one way, it could mean, well, we have to list 8 twice. And if we were doing it that way, then we'd also have to list the -7 3 times. But do we really have to? Well, since we're just saying what the zeros are here, you don't actually have to list them out separately like that. It's okay if you just say that x equals 8 and -7 here. Now, later on, after you've been doing these more, especially in pre-calculus, you'll actually see where some of that's going to come into play more, and you will need to know what the multiplicity of a 0 is. That's the fancy name given to the fact that 8 came up twice and the -7 came up 3 times. That's their multiplicity, because it affects the graphs and some things like that. But for now, when just saying what x would equal, you don't have to list the duplicates. But you can if you want to. All right, and then for the last one then, it follows on the same ideas of what we've just been doing. And so from the first part of that, we have the 3x squared. What can I plug in for x that makes that equal 0? 0. Yep, because 0 squared is 0 and 3 times 0 is 0. And then we repeat the process for the parentheses as well. We say what plus 4 equals 0. That gives us -4. And then 2x minus 5, what makes that equal 0? Well, that one's not 5 though, is it? Because we're actually having to figure out what makes 2x minus 5 equals 0. And if we solve that out, like if I add 5 to both sides and then I divide both sides by 2, I end up with 5/2 or 2.5, or if you prefer decimal, 2.5. Any of those forms work, but you do have to account for the fact that we have that 2 sitting out front when you get that answer. All right, now that we've seen how we can go from the equation and find the zeros nice and easy, it's a fairly straightforward process. And so I figured that you should then be able to take a list of zeros that I give you and write the equation that would give us those zeros. And so that's what we're going to do next, is I'm going to give you a list that looks like this. Your answer is going to look like this sort of equation that we were just creating here. So here are our 4 lists of zeros. For each list, please write the polynomial function that would give us those as zeros. So for that first one then, we want to say, okay, what's going to make it have a 0 at -3? Okay, so that means that I have to do something to x that makes it so that when I plug -3 into it, we get 0. So that means we have to add 3 to it. And so you'll end up with the x plus 3 there. So that same kind of sign flipping pattern you'd probably noticed on the previous page, right? You go ahead and do that for all 3 zeros, and so you end up with 3 sets of parentheses. All right, for the next one there, we have -5. Okay, that's going to be x plus 5, but 0. If we want one of the zeros to be 0, what do we plug in? What's in our equation? Yep, it's just an x. You might be tempted to say like x plus 0 or x minus 0, but we don't need to do that because that just equals x. Now, if you wrote it out in the same order, though, that the original was in, this is what you would write. But it looks slightly awkward, especially because depending on how your eye is trained, you might be looking at this and thinking that it means multiplication, because it is awkwardly in the middle. And so in order to remove that ambiguity, it generally is better to go ahead and write the x first instead of just putting the x in the middle. All right, for the next one, we have the -4, that -4, listed 3 times. And so you will have x plus 4 in there, but that means that you would have x plus 4, x plus 4, x plus 4. I don't want to really have to write x plus 4 3 times, so go ahead and write it as x plus 4 cubed. Notice here, they're telling us that it needs to be cubed by including the multiples. All right, and then for that last one, same basic idea. We have zeros, which I know comes from x, but since there's 2 zeros, that tells me to make it an x squared. And then we have 3 of the 1s. The 1 would give me x minus 1, so this is going to end up being x minus 1 cubed. And then, of course, the x minus 8 still hanging out there. Now, in this case, I gave kind of the most basic answer for each of these, but there's actually a lot of different variations of each of these that you could make. Because, for instance, like on that last one, what if I multiplied it by some constant? What if I multiplied the whole thing by 3? It would still give the exact same zeros, right? And so you can go ahead and multiply any of these by a number like that. However, why wouldn't I do it? Why add more complexity if we don't need to? Okay, so if we don't need to put in that extra little bit, I tend to skip it. The last problem we're going to be taking a look at is this one. 0 equals x to the 8th minus 17 x to the 4th plus 16, which sounds kind of familiar, doesn't it? That's the problem that we started class with, yep. The difference is that that was y equals and this is 0 equals. And since it is now 0 equals, that means we can solve it, whereas we couldn't solve it when it was just y equals. Now, remember when we did quadratics and solved quadratics? In order to solve a quadratic, our first step that we did is we would try to factor it if we could. Because if you could factor it, it was really easy to find the answers just from the factored form. Just like we've been practicing with those polynomial zeros, same thing here. And so, does this one factor? Yes. Oh yeah. That's what we did at the start of class, right? That's why I had you do it at the start of class. Was so that we could go ahead and skip now that whole process of factoring and already have it factored, so now we can focus on the solving. And so when we go to find our solutions now, again, there are going to be zeros because the whole thing is set equal to 0. I need to look at each set of parentheses and decide what the solutions would be. But you're going to notice, because of the type of factorization that's involved here, we will have some solutions in some places, but not necessarily in all of them. So let's start here. The x minus 1. Can we solve that? Can we make that equal 0? Yes, we can. And so we can go ahead and solve that one. And we can solve the x plus 1. We can make that one equal 0 as well. What about the x squared plus 1? Can we solve that? Well, let's actually go ahead and do the algebra on it. What if I actually want to take x squared plus 1 and set it equal to 0? Okay, so we'd subtract 1 from both sides, so x squared equals negative 1. Then we take the square root of both sides, which will give me the plus or minus, remember this plus or minus when you take the square root, of negative 1. What's the square root of negative 1 equal again? Yeah, it's I. Which stands, of course, for imaginary. It's an imaginary number. Do I need to include the imaginary solutions here then? Well, this is the good news time for you. From here on out, if a problem does not say to include imaginary solutions, you don't need to. Okay, so just because you know imaginary numbers doesn't mean that all of a sudden you're going to have to go back to everything you ever learned before and redo them as imaginary. And so when we say solve, we're assuming only real solutions. So x squared plus 1 will not give us any solution because it would give us imaginary. So then let's keep looking through. The x minus 2, will I get a solution there? Yes, because it's just an x. What about the x plus 2? Will we get a solution there? Yes, because again it's just an x. What about the x squared plus 4? Will we get a solution from that one? No. Because again, if I try to solve that one, I'd have to subtract 4 from both sides and take the square root of a negative, which we can't do. And so we can solve something as complicated as a degree 8 polynomial. However, we can only do so, at least right now, by factoring. And by using these factoring techniques that we introduced yesterday, we can break stuff down actually quite a ways in order to deal with something as complicated as this and go ahead and get those solutions.